Well, thank you for the nice introduction. Okay, so the majority of this work was done jointly with Ronald Dehaan and Stefan Seider at the Vienna University of Technology. There are some very recent updates that I included here, which basically is joint work with Mathieu Lidloff and Johan Todinka at Université d'Orléans. So here's the outline of my talk. I'll start with the standard CSP, in which we're talking about relational constraints. And I'll describe what restrictions and structural parameters we look at, and I'll describe our results and assumptions. And then I discuss the CSP with global constraints. We focus on two types of constraints, the compressed table constraints and the cardinality constraints. So I'll describe our results for each type of constraints, and I'll conclude with some open questions mainly pertaining to CSP with cardinality constraints. Okay, so we start with the CSP, in which basically the constraints are relations. So an instance of constraint satisfaction problem is given as a triple set of variables V, a set of domain values that those variables can be assigned values from, and a set of constraints C. Each constraint is given as a pair consisting of a sequence of variables S and a relation over domain values whose arity matches the length of S, the number of variables in S. So an assignment is a mapping from the set of variables to domain values. And we say that an assignment satisfies a constraint if the values assigned to the variables in this constraint is a tuple in the relation of this constraint. And we say that an assignment satisfies the instance if it satisfies every constraint in the instance. And an instance is satisfiable if there is an assignment that satisfies it. CSP is the problem in which we're given an instance and we asked if there is a satisfying assignment. So here are some of the restrictions and structural parameters that we focus on. By Boolean CSP, we denote the CSP with the Boolean domain. Our CSP denotes a CSP of bounded arity R, meaning each constraint contains at most R variables. And the tuples, so this parameter is going to denote the total number of tuples in the instance. Const is going to denote total number of constraints. Dom is going to denote the domain size. Degree is going to denote the maximum number of constraints any variable appears in, just like in satisfiability problem. And the arity is going to denote the maximum number of variables any constraint contains. Okay. Now, there are two kind of popular graphs, auxiliary graphs, that have been associated with CSP, also with CNF-SAT. The first one is the primal graph. The vertices of this graph are the variables in the instance, and there is an edge between two vertices if they occur together in a constraint, in the same constraint. The incidence graph is a bipartite graph. On one side you have the variables, and the other side you have the constraints, and there is an edge between a variable and a constraint if the variable appears in the constraint. TW denotes the tree width of the primal graph, and TW star denotes the tree width of the incidence graph. Okay, so it's obvious to see that a CSP instance on n variables can be solved in time domain to the number of variables by trying all possible assignments. Okay, so that's like a brute force trivial algorithm. Significant work basically was considered trying to improve this brute force algorithm. They could only improve in the base of this exponential term. So for example, for certain restrictions like binary CSP, you could do something like domain -1 to the number of variables. Okay, but there hasn't been any improvement really in this to bring this linear to a sublinear, basically, exponent. Okay. So a natural question to ask is, can this exponential term, domain size number of variable, be reduced to a sub-exponential factor, meaning domain to little of number of variables, possibly considering various natural restrictions on the CSP problem. So this is what we try to do, try to investigate the sub-exponential time complexity of CSP with respect to some restrictions and some of the structural parameters that I already described earlier. And for several of these parameters, we were able to obtain threshold functions that precisely dictate when and when not the problem is solvable in subexponential time, in the sense that below this threshold function, the problem is solvable in subexponential time. Above it, it's unlikely to be solvable in subexponential time. So this allows us to kind of draw a detailed landscape of the subexponential time complexity of CSP with respect to those restrictions and the structure parameters that we consider, in parallel to similar work for CNF-SAT, like in terms of the clause density or frequency or the width of the clauses, stuff like that. Now, most of our negative or lower bound results are derived under common assumptions in complexity theory, such as ETH does not fail, W hierarchy does not collapse at a certain level, and CNF-SAT is not solvable in subexponential time. Okay, so to kind of translate some of those lower bound results for that we already know for CNF-SAT, we kind of establish a connection or reductions from CNF-SAT's restrictions of CNF-SAT to CSP and restrictions of CSP. So this allows us again to translate some of the lower bound results that we already know for CNF-SAT to CSP. So naturally, CSP seems a more general problem than CNF-SAT in the sense that an obvious way of modeling CNF-SAT as a CSP is to look at every clause and model the clause as a constraint containing all the tuples or the values that basically assign to the variables of the clause that satisfy the clause. Okay, so that's a natural way of looking at CNF-SAT as a CSP problem. Okay. So using this kind of trivial, modeling, we immediately can obtain the following result. So the theorem is stated in terms of Boolean, but it could be stated in terms of any bounded domain size. So basically, the theorem says that the subexponential time complexity of Boolean bounded arity CSP is basically the same as the subexponential time complexity as KCNF-SAT. So you could solve this problem in subexponential time if and only if ETH fails. Okay, and again, for any bounded domain size, the same result holds true by encoding the domain size using binary variables. You can see that. So this is very easy to see if on one basically direction, if you look at, let's say, look at 3 CNF-SAT, right? Then again, every clause, because it has width at most 3, can be modeled as a constraint, and you can enumerate all the tuples that satisfy it in constant time, basically. So you could transform an instance of 3 CNF-SAT to an instance of CSP on the same number of variables, basically, and that's like a polynomial time surf reduction. Okay. On the other hand, also, because you have bounded domain size and bounded arity, you could take every constraint and encode it using, a constant number of 3 CNF clauses. Okay, and it's still using the same set of variables. So this gives you both directions here. That's very easy to see. Now, what we show is if you drop the bound on the domain size, so you allow unbounded domain size, but keep basically the upper bound on the arity, even if you consider basically binary CSP, then we give evidence that the problem now seems to become harder in the sense that if you could solve binary CSP in subexponential time, then you could solve clique in time n lit low of k. So, of course, if clique is in n lit low of k, this implies that ETH fails. Okay, but the other direction is not known and basically is not believed to be true in general. Okay. So now, on the other hand, if you look at Boolean CSP, so bounded basically domain size, but allow unbounded arity. So what we could show is the following result. If you could solve Boolean CSP in non-uniform subexponential time, then you can solve CNF-SAT in non-uniform subexponential time. Now, why is this non-uniformity here? Well, again, we said that CSP seemed to be more general than CNF-SAT, but the problem really is in the representation of CSP, because if you take a clause in CNF-SAT and you want to basically encode it as a constraint, then you need to enumerate all tuples that satisfy this clause. Now, if the width of this clause is linear in n, then to enumerate all tuples, you need exponential time. So if you're trying to achieve a sub-exponential surf reduction from CNF-SAT to CSP or to Boolean CSP, you cannot afford to enumerate all tuples. However, what you could do is you could start by applying a branching algorithm due to Schuller that reduces the width of each clause from possibly linear to, if you have linear width clause, to sublinear. Okay, and then after reducing it to sublinear, now you could basically enumerate all tuples. Okay, but in order for this branching algorithm by Schuller to kind of run in sub-exponential time, you need to know that the number of clauses is somehow sub-exponential. Okay, if the number of clauses in the CNF instance is exponential, let's say larger than 2 to some c times n, where this c now, there's a relation between the sub-exponential time that you're trying to achieve and this c, then you could afford in that case, if its number of clauses sub-exponential, to run Schuller's algorithm, then basically model each clause as a constraint and everything will go through. However, if the number of clauses is exponential, then you cannot afford doing that. But in this case, what you know is if you use the brute force algorithm, because the instance size is exponential in n, then this brute force algorithm would run basically in polynomial time in the instance size. However, that polynomial, the exponent of that polynomial depends on the epsilon that you're trying to achieve. So that's why for every epsilon you're trying to achieve, you get a different polynomial basically, and this is hence the non-uniformity in this reduction. So this is what we could show in this case. Okay, so kind of to just summarize or highlight the results that we obtained for CSP with respect to the different structural parameters that we looked at. So here in blue you have the positive results, in red you have the negative. The negative results are under the assumption that ETH does not fail. So we could show if the number of tuples is sublinear, then the problem is solvable in sub-exponential time. If it's linear, it's not. If the number of constraints is constant, the problem can be easily shown to be NP. It's known to be NP. If the number of constraints is little omega of 1, it's not solvable in sub-exponential time. If the degree is 1, the problem is NP. Degree greater or equal to 2, the problem is not solvable in sub-exponential time. For arity, if the arity is 1 or if the arity is 2 and the domain is at most 2, the problem is known to be NP. Otherwise, it's not solvable in sub-exponential time. In terms of the primal tree width, if the primal tree width is sublinear, the problem is solvable in sub-exponential time. If it's linear, it's not. If the incidence tree width is a constant, the problem is NP. If it's omega of 1, the problem is not solvable in sub-exponential time. So this is basically a summary of the results that we obtained for the standard CSP. Okay, so now I kind of move to talk about the CSP with global constraints. So in the CSP, the constraints are given extensionally as tables or relations. In CSP with global constraints, the constraints are specified intentionally using some property, basically, that you need to satisfy in order for the constraint to be satisfied. Now, we consider two main categories of global constraints. The first category is cardinality constraints, and there are different types that we consider. We have the CSP with all different constraints that we denote CSP different, CSP with exactly n value constraint, we denote CSP equal, at least n value, CSP greater or equal, at most n value, CSP less than or equal. And also for several of our results, you could allow a combination of those constraints. Okay. And the other category that we consider is CSP with compressed table constraints, CSP-C. I'm going to describe what those are. So in CSP with global constraint, the goal remains to find an assignment that satisfies all the constraints, but satisfying now a constraint takes a different meaning. So for the CSP all different, a constraint is satisfied if its variables are assigned distinct values. For the CSP equal, CSP less than or equal, CSP greater or equal, each constraint is given together with a non-negative integer, nc. And the CSP equal constraint is satisfied if the number of distinct values assigned to its variable is exactly this number, nc. And the less than or equal constraint is satisfied if the number of distinct values assigned to its variable is at most nc, and the CSP greater or equal, a constraint is satisfied if the number of distinct value is at least nc. For CSP with compressed tables, a constraint there is given, again, as a pair consisting of a sequence of variables and a set of compressed tuples. Each compressed tuple is a sequence of subsets of domains of these variables. So V1 is a subset of domain values of variable V1. VR is a subset of domain values of VR. And a constraint is satisfied if its variables are assigned values that basically that correspond to a tuple and the cross product of one of these compressed tuples. So you could kind of decompress, if you want, each one of those compressed tuples to obtain a table, and now you have basically the CSP back in this case. Okay. Now it's known that all those aforementioned CSP's global constraints are NP-complete. Some of them are even NP-complete for one constraint, even when you have one constraint. So why do we consider CSP with global constraints? First, they seem to be very important in practice. They do model many NP-hard problems. And the reason why they're important in practice, especially people use combinations of those, because they kind of give you a more compact representation of these constraints. So for instance, the CSP with compressed table can potentially provide exponential reduction in the size, because really you're reducing the cross product, or all the elements in the cross product. So now if you could represent them as basically the sum of the cardinalities as opposed to the product of basically the cardinalities here. Now, those CSP with cardinality constraints, on the other hand, they naturally model many graph coloring problems. So the CSP with all different constraints, even if you look at the binary CSP with all different constraints, it can model graph coloring. And in general, you could model different types of hypergraph coloring problem, where you want to say for each hyperedge, I want it to be assigned exactly this many colors, or its vertices to be colored with exactly this many colors, or at least this many colors, or at most this many colors. So they naturally model many of those coloring problems, as you'll see shortly. Okay, so start by highlighting some of the tight results that we get for CSP with the compressed table constraints, and then we move to the other CSPs, global constraints, which are CSP with cardinality constraints. So clearly this CSP with compressed table is a generalization of CSP. You could look at CSP as a CSP with compressed tables, in which basically each one of those sets of domain values is a singleton. Okay, and for CSP, we already saw that we know if Boolean CSP is solvable in sub-exponential time. Of course, ETH fails, but we also say that if it's solvable in non-uniform sub-exponential time, then CNF-SAT is solvable in non-uniform sub-exponential time. So we do have such results already for Boolean. So one can ask, what can we say now about the Boolean CSP with compressed table? Okay. So we kind of give evidence that it's harder than Boolean CSP. What we show is if you could solve Boolean CSP with compressed table in sub-exponential time, then the W hierarchy collapses at the second level. Of course, this result, W2 equal FPT, implies that CNF-SAT is in sub-exponential time. Now, in terms of, again, the results that we get with respect to those structural parameters described earlier, we get actually a table that more or less matches the table that I showed you earlier for CSP. So all these results seem to kind of carry over here without really any major changes. Okay, Okay, so now we move to those CSP with the cardinality constraints, and we start with the CSP with all different constraints. So again, recall here that all different constraint is satisfied if all the variables receive distinct values in the constraint. So you could easily see that the problem can be modeled as a list coloring problem, where the vertices of the graph are the variables of the instance, and each vertex is its list of colors is basically the values in its domain. And now two vertices are adjacent if they appear together in the scope of the same constraint. Okay, so this gives us basically a simple reduction from CSP all different to list coloring. Now we know that list coloring is solvable in time 2 to the n, so this tells you that CSP all different is solvable in time 2 to the n. A direct consequence of this is that if you look at any domain size that's little omega of 1, then you can say that CSP all different is solvable in sub-exponential time in this case, because 2 to the n becomes domain to the little o of n if the domain is omega of 1. So this tells you for any domain size that's not a constant, the problem is solvable in sub-exponential time. So now you could focus really on constant size domain. If the domain is 2, then the problem is known to be in P in this case, so you can look at domain greater than 2. And just to highlight some of the tight results again that we get in this case. So for domain, again, that's little omega of 1. The problem is trivially in sub-exponential time by this list coloring reduction. And if the domain is greater or equal to 3, it's not in sub-exponential time under ETH. Now, if the number of constraint is linear, it's not in sub-exponential time. In this case, because the domain size, as I mentioned, is bounded, it doesn't make sense to consider the number of constraint to be sublinear, because if the domain size is bounded, then the arity is bounded, because you're looking at all different, which implies basically that you need a linear number of constraints to account for all the variables in the instance. So if the primal tree width is sublinear, the problem is in sub-exponential time. If it's linear, it's not. Same thing holds for the incidence tree width. All right, so with respect to the remaining cardinality constraints, what we could show, again, is the tight results that we could show is in terms of the primal tree width, if kind of the same results for all different hold true here. If the primal tree width is sublinear, the problem is sub-exponential time. If it's linear, it's not. And finally, with respect to the number of constraints, we could show that all these problems are unlikely to be in sub-exponential time, again, under ETH, when the number of constraints is linear and the domain size is constant. On the other hand, if the number of constraints is sublinear, then all these problems are solvable in sub-exponential time. And this is some of the very recent result that we obtained. Here you use kind of dynamic programming to get this sub-exponential time algorithm. Okay. So just want to conclude with some open questions really that are related to these two theorems here, and also to some of the earlier discussions here at the workshop, mainly to the talk given by Fedor Fumin the first day of the conference. So again, for this cardinality constraint, we showed that if the number of constraints is sublinear, the problem is solved in sub-exponential time. But now, if the number of constraints is linear, the only hardness results that we could show is when the domain size is constant under ETH. Because really, you could reduce 3 colorability here to this problem in this case to get the lower bound result. So I think the interesting questions here that remain here regarding this topic is what happens if the domain size is not a constant and the number of constraints is now linear. Okay, so in particular, what if you talk about a number of constraints that's linear and the domain size that's linear? So now the problem really is like you're assigning these n variables to, domain values, and the size of the domain is linear. So you have this mapping from linear size to linear size, and you have also a linear, or at least a linear number of constraints where you could encode, basically, use to encode problems with. Can you still get a sub-exponential time in this case? Or on the other hand, can you use some of those recent lower bound results based on graph homomorphism? Because you could see maybe you could try to model graph homomorphism using these kind of cardinality constraint CSP here to get a lower bound result. But the difficulty seems is those cardinality constraints, they're kind of restrictive in what you could use, what you could encode with. So if you try to encode a graph homomorphism problem, at least from the first attempts that we tried, you kind of end up increasing the number of variables to quadratic. So you don't get a surf reduction. So I think a natural question here to either basically show that still can do sub-exponential time in this case, or try to kind of, under ETH, maybe rule out the possibility for larger domain size. Okay, so that concludes my talk. Thank you for listening.
Any questions? Patrick Truxler's result?
I think so. 2014 or 8? 8, yeah. Mm-hmm.
to do this?
Well, I think he used a different representation for CSP, not the standard representation. I believe he used like a DNF representation of CSP. But yeah, it's a different way of representing CSP, yes. If I got what you're talking about, yeah.
Yeah, what is your opinion about when both cons and dom are linear in end? Do you expect it to be sub-exponential or not?
Actually, I don't know. It could go really either way. I mean, I don't know. I don't have a strong feeling about this. I mean, these cardinality constraints seem to be, again, very restrictive when you try to encode problem with, because you just say, well, in this constraint, I need to assign at least this many distinct values. So, like, we tried to encode graph homomorphism with them, but we couldn't. Maybe there is a kind of a clever dynamic programming algorithm where you could still get sub-exponential time in this case.
Well, thank you.
So currently you have a C to the little square of n lower bound of this kind of.
Little of square.
And you mentioned you had this lower of n square. Didn't I get it right? With the self-reduction you tried for this last problem, the last.
Here?
When both are n, what was the next?
When both the number of constraint is n and the domain size is n?
Yeah.
We don't have, again, any end result. That was like an open question of whether you could do sub-exponential time in this case or not. So sub-exponential in this case, when both are linear, is n lit low of n. You're asking, can I do n lit low of n when the number of constraints is linear and the domain size is linear? You know, this is why I'm saying maybe you could use this lower bound on graph homomorphism to say under ETH, I cannot get n lit low of n in this case.
Thanks, Iyad.